We're pretty much done with chapter 20. I think. Did I miss anything? No. And so we're going to start the 24, but there's a couple of things from the earlier chapters between 21 and actually 21 through 23. I just want to talk about metals. 24 deals with transition metals. And we're going to look at some properties of metals. One, we're interested in optical, right? And what else?
Professor, is this chapter 24?
No. Electrical and magnetic.
Are you recording? Are you recording?
Yeah. Some of this is in chapter
Just so that we know.
12, the end of chapter 12. Electrical properties. Let's just start off with electrical. And then we'll see about the optical. Electrical properties, at the end of chapter 12, there's something called band theory, which I pretty much skipped in 1A. Normally it's covered in 1B. And so I'll show you some figures for these. Yeah. But basically, it's MO theory for solids. And so when you build up a solid, there are a lot of atoms. So let's say if I have a lithium atom here, this would be an atomic orbital, another atomic orbital. Lithium is what has the valence 2s. So we have a 2s orbital here with 1 electron, 2s orbital here with 1 electron. And so let's just look at the valence atomic orbitals. When we bring these together, we're going to get 2 MOs. Do you guys remember the way we name MOs? What would this kind of MO be? It's built from 2s orbitals. Sigma, yeah, it'd be a sigma orbital. This would be a sigma 2s because it's built from the 2s. This one would be a sigma star 2s. So we got the bonding and the anti-bonding. That's from 2 orbitals. But it happens if we have more than 2 lithium atoms. So we could extend this out further. So let's say I have 2 lithium atoms here. And this would be for Li2. Let's combine it with 1 lithium here. And so what we end up with is MO requires LCAO. What does LCAO stand for? Linear combination of atomic orbitals. We only combine 2 atomic orbitals to form 2 molecular orbitals, right? And so this third MO becomes what we call non-bonding. And so there are actually 3 types of MOs. There's the bonding. Actually, is that right? Yeah, bonding. This is anti-bonding. And this middle one, which isn't combining with anything, right, is a non-bonding MO. Well, we could fix that non-bonding MO by bringing in a 4th lithium. If we bring in a 4th lithium, what's it going to look like? It's going to look something like this. This would be Li3, sorry. 3. If I have 4 lithiums, then now I can do 2 LCAOs. With 2 LCAOs, I'm going to form 2 sigma bonding and 2 sigma anti-bonding. They aren't actually going to be at the exact same energy because of what happens when we get this scenario here. And so here, this is sigma, this is sigma star. This would be for Li4, 4 atoms in that cluster. All right, one of the properties of this we could see would be its optical properties. When we're talking about optical properties, what am I asking? I'm asking how it interacts with light. And so how does matter interact with light? Well, in different ways, right? How do the electrons of matter typically interact with light? With photons. And electrons usually interact with what energy photons? Would you say that in other words, do they interact with infrared photons, typically? Do they interact with what
Visual light?
visible? Normally when we think about what we call electronic transitions, you know, so here I have 1 electron each in here, so that's going to give me 4 electrons, and I fill these up. Then like a visible photon will come in, hit this electron here, and they'll be excited to higher state. That's what we mean by optical properties. And so typically that requires visible light because of what we call the energy gap. You know, this is the energy gap here. The energy gap is typically in the visible region for lots of matter, but not all matter. You know, can you think of some matter that interacts with radio waves, for example? Is there some matter that interacts with radio waves? I think I got the wrong chapter. Metals. Metals interact with radio waves. Now, are radio waves high energy light or low energy light? Low energy light. So, well, typically when we're talking about metals, we're talking about extended solids, right? We aren't talking about clusters of 4 atoms. We're talking usually about lots and lots of atoms. And so when we look at something like this, let's see, this is carbon. Let's see if I have lithium here. Yeah, here's lithium. Here's one. I have 1 lithium. I have just an atomic orbital, but if I have 2 lithiums and I get molecular orbitals here, the sigma star. 3 lithiums, and we could throw in the non-bonding orbital right in the center here. That's not doing an LCAO. But when I take an Avogadro's number of lithium atoms, what happens is I form Avogadro's numbers worth bonding and anti-bonding orbitals. And you see what happens is these orbitals are very tightly packed. And so you got an Avogadro's numbers worth within here. It looks as if it's a continuous band of orbitals. And so we call this a band here because the gap between one energy level and the next is negligible. And so something like a metal, like lithium, would have half of this filled, right? The other half, which is the antibonding, just kind of extends down in there. And so something like lithium metal can absorb radio waves because it doesn't take much energy to promote an electron here. In fact, thermal energy is enough to promote an electron up here, which makes lithium an excellent conductor of electricity, because in order to conduct electricity, let's look at the electrical properties. And so this is what we end up with here. What we end up with is something like this, where we got, n lithiums. Let's do n Avogadro's numbers worth of lithiums and another Avogadro's numbers worth of lithiums. And then let's color code this. And so the bonding orbitals are going to form a cluster or band of molecular orbitals. call a band of molecular orbitals. This band of molecular orbitals is like this. You know, energy is quantized here, but you know, even though energy is quantized here, the gap between one orbital and the next is so small, it's pretty much behaves as a continuum. And then the antibonding orbitals are the same. This. And so this just forms one whole band pretty much. And so lithium is what we call a half-filled band. Half-filled band should conduct electricity quite easily, because what happens in a half-filled band is that electron sitting up here is easily popped up here into an empty orbital. Once it's in that empty orbital, molecular orbitals span the entire solid, and so it's got high mobility.
Professor, why is one blue and the other one red?
Because this one's coming from the antibonding and this one's coming from the bonding, and they're overlapping. That's what we call overlapping.
So,
MOs.
does the band only happen in metals?
No. The band happens in solids, all solids. So for example, if you were to look at diamond, although they didn't show diamond here, we could see diamond. If we would look at diamond, diamond is just an array of carbon atoms. You know, so we take n carbon atoms here, n carbon atoms here. But the problem is the bond is quite strong here. And so when we look at this band of bonding MOs here, it doesn't quite reach up to the antibonding MOs here. So you got a bunch of antibonding MOs forming a band here. And there's a gap here between the bonding MOs and the antibonding MOs. This is called the band gap. For diamond, you know, the band gap is around the UV range. And so visible light, you know, are diamonds colored? No, diamonds are colorless, right? They don't absorb visible light. They don't absorb any visible light because visible light doesn't have enough energy to promote an electron. You need UV to overcome this huge gap here. Typical, even like something like sodium chloride even has a pretty big gap. Things that are insulators have big gaps. And so diamond is an insulator. We give names to these bands. Like this bonding band here is called the conduction band. Or no, sorry, not the conduction, the valence band. And so this is filled with diamond electrons. Up here is an empty band, the antibonding band. This is called the conduction band. It's called the conduction band because if you can get electrons up here, you know, these are empty orbitals. And if they're empty orbitals, then they can conduct electricity from one end of the crystal to the other end of the crystal. And so here, the band gap is about UV. What's the band gap over here? Here, the band gap is 0, pretty much. You know, the band gap is tiny. The band gap is so small that just thermal energy, 25 degrees Celsius, is enough to pop an electron up here. And then, you know, metals can absorb radio waves, which just means it pops it up higher. Metals also have, you know, metals, what color are metals? Well, tiny crystals metals, they're black, right? Black means what? They absorb all colors. They absorb all colors because this is a wide band, and so it could absorb a continuum of colors. If it absorbs the whole rainbow of colors, then it's black. And so metals are kind of funny because in one sense, metals, the electron energies in metals is continuous, not quantized. In another sense, the electron energies in metals are quantized. In reality, the electron energies in metals are quantized, but the spacing between the orbitals is so tight, it's a continuum. That's why things like iron behave like black bodies, right? You guys remember black bodies? Mm-hmm. Right, and so metals, extended solids of metals will behave like black bodies because black bodies absorb all energies and emit all energies. And if you look at this band, it should absorb all energies, emit. Because here, radio, infrared, visible, UV, etc. There are some things that conduct electricity when you shine light on them because of the band gap. It depends on what kind of light. I mean, you can make diamond conduct electricity if you're blasting it with UV. It will be a better conductor of electricity. But diamond's what we call an insulator. So metals are going to look black, or they're going to have a silver luster to them. They reflect all the colors, absorb and emit all colors of light. Semiconductors, on the other hand, typically have a band gap in the visible region. And so when we're looking at the gap between the conduction band and the valence band here, this is typically in the visible region. And so semiconductors are going to have a color to them, like germanium has a distinct color, or a lot of these other things will have a color associated with it. Silicon's black. Silicon, infrared isn't a promoted electron here, and visible is completely absorbed. And so with the semiconductor, what happens is, you shine light. A photon of light comes here, hits an electron, promotes the electron up here, and then it starts to conduct electricity. If there's no light, then it shouldn't conduct any electricity. But it would be light-induced conductivity. Electrical conductivity we can understand this. Electrical conductivity is proportional to N mu E. N is the number of charge carriers. Mu is the mobility of those charge carriers, and E is the charge on the carrier. And so the charge carrier can be electrons or ions. They have to have some mobility, and we have to have a lot of them. And so semiconductors don't have a huge electrical conductivity because we only promote a limited number of electrons up here. Metals have a very large number of charge carriers. We can increase the conductivity of a semiconductor. Do you know how we can increase the conductivity of a semiconductor? This is what we call an intrinsic semiconductor here. Intrinsic. Like germanium. One way we can alter the conductivity is by doping. What doping is just introducing small amounts of impurity that causes defects, which causes the electrical conductivity to increase dramatically. And so, for example, we could look at phosphorus-doped germanium. This is what we call a we call this an N-type. N-type. You don't have to know these words. N-type. And so if we take that intrinsic germanium here, we got this pretty big gap here. But if we were to introduce phosphorus atoms here, what does that do? Well, germanium is tetrahedral. The germanium should be sp3. But phosphorus, phosphorus wants to bond either 5 or 3. 3 bonds in a lone pair, or 5. If it bonds 4, that leaves what we call a dangling bond, or like a free radical, right? And so if we only bond 4, why bond 4? Why doesn't it bond 5 or 3? Because it's stuck in this germanium crystal, and germanium's all sp3, tetrahedral. And so we got this phosphorus here. Well, is this electron bonding? No, this is what we call non-bonding electron. Where do the non-bonding electrons usually hang out? They usually hang out in the middle here somewhere, right? But in this case, it turns out that this non-bonding electron here is just right below the conduction band in terms of energy. So we got a non-bonding electron, depending on how many phosphorus. So here's one phosphorus, here's another phosphorus, here's another phosphorus. And so let's say I have 3 phosphoruses incorporated. I'm going to have those 3 non-bonding electrons there. Now, this gap here is visible, but what do you think the gap is between this? This is what we call an atomic orbital, because this would be an atomic orbital, right? Oh, we don't have to worry about that, but what do you think the energy required is to promote an electron from this localized, this is what we call a localized electron, promote it from a localized orbital. If we promote it up here, then this is an MO. MOs are delocalized orbitals. And so how much energy do you think it requires to promote that? Thermal. Nothing, basically. And so an electron gets promoted up here. So take that electron, promote it up here, thermal energy, and then what can that electron do? Start conducting electricity. And so all these will do that. Here.
Visible light.
No. Thermal energy. Visible light is still promoting electrons from down here. This is visible. This is thermal. Very little energy is required to promote it. But this extrinsic type conductivity is much, much higher than the intrinsic. And so what you can do is, by doping this, you can increase the electrical conductivity by substantially, by large margins. So And depending on how much you want to dope in there, you can alter the electrical conductivity of this. So that's phosphorus doped. Germanium, we just introduce a phosphorus in there, but we could also introduce something like boron. So let's look at boron. Dope. Germanium. Boron, how many bonds does boron want to form? Well, how many valence electrons does boron have? Three. And boron's going to be stuck in what type of lattice? An sp3 lattice. So if you hybridize boron as sp3, that leaves one empty sp3 orbital. Okay? And so this germanium here is going to have a localized electron there, but let's see, there's going to be a germanium here. And so what that does is we got this sp3 orbital that's empty here. And so what's going to happen is this empty orbital resides just above the valence band, depending on how many borons we have in there. So let's say I have a bunch of borons in there. Here. And these are localized. And so what can happen here is an electron can be promoted from the valence band up here. When an electron is promoted up there, it leaves behind what we call a hole, a charge imbalance, like this. A hole. Is there such thing as, is there such an entity as a hole? Is a hole an anti-electron? Is it? So we have these holes here that are anti-particles. No, it's just an imbalance. All of a sudden we have more protons than electrons. And so even though it's an imbalance, there's something funny that happens. And we call this a p-type semiconductor because the n-type deals with the charge on the carrier. N-type means negative charge carrier. A negative charge carrier because electrons are conducting electrons. Here the electrons can't conduct because these sp3 orbitals are localized, not delocalized. And so what can conduct? Well, the holes. Well, how do holes conduct electricity? And so this is a positive carrier. Well, the only way holes can conduct electricity is if an electron jumps from one hole to the other, isn't it? That would seem, and then it would seem like the electrons are the charge carriers, but in reality, you can tell the difference between a p-type electrical conductivity and n-type electrical. It actually can be measured. And so there's an actual measurable difference between electrons conducting and holes conducting in terms of something called the Hall effect, deals with magnetic properties. So here is a little summary kind of thing. A lithium would be like B, where what we call the bonding and the anti-bonding overlap. In other words, the valence band and the conduction band overlap. Like that, there's zero band gap. C is the semiconductor with a band gap in the visible region typically. D is an insulator with a large band gaps like diamond. A is what we call a half-filled valence band. If you have a half-filled valence band, then it takes no energy to promote an electron up to the next higher energy orbital in there. And so a half-filled valence band or zero band gap will conduct electricity very well. And so the way we define metal, semiconductor, and insulator is by electrical conductivity. And it has to have electrical conductivities within certain ranges to be classified as this. All right, we talked about the N-type semiconductor and P-type semiconductor by doping. These are called extrinsic versus the intrinsic. And then you can make devices. If you put a P-type sandwiched with an N-type, you can make a voltaic cell. As you generate electrons, one side and the other. So this would be a photovoltaic cell. You don't have to worry about the operation. But again, we see the anode, we're generating electrons at the anode. They're going to be consumed by the cathode, which is the P-type, and the N-type would be the anode.
So it's just two silicons? Different types?
Well, yeah. This one, your traditional cell.
This is chapter 11, actually.
Yes, sorry, this is chapter 11, not 12. That's a section in chapter 11 I skipped in Chem 1A. I'm talking about it now. This type of stuff that I'm talking about right now is that here. Okay. We talk about certain things, like electrical conductivity and temperature. What do you expect to happen, in metals? As the temperature increases, do you expect the electrical conductivity to increase, decrease, or to stay the same? What do you think? As the temperature increases, the electrical conductivity of a metal decreases. Do you know why it decreases? Because because the hotter it gets, the more vibrations you have, and the more the electron path is impeded through the solid. And so it turns out is if you can get the metal cold enough, so that the vibrations are minimal, the electrons have a smooth path from one side of the crystal to the other. And so there's a certain temperature at which metals will display unusually high conductivity. This unusually high conductivity is called superconductivity, and so metals will superconduct at very low temperatures. As the temperature increases, the resistance the electrons encounter will increase. How about semiconductors? Would you expect the same thing for semiconductors or the opposite? Actually, the opposite for semiconductors, because semiconductors are relying on these defects. So the higher the temperature, the more electrons you could promote, and we need that promotion of electrons to conduct the electricity. And so for semiconductors, typically, you'd expect an increase. And the same thing with insulators, because insulators you might at higher temperature introduce defects, but insulators can be more tricky. Now, let's see. Here's a superconductor. This is a ceramic, though. And this is kind of interesting because at higher temperatures, this doesn't conduct electricity at all, but at very low temperatures, this will start to conduct electricity. And superconductors, these things expel magnetic fields. So if there's a magnet here, you can make it levitate. And, this is the yttrium-bearing copper oxide. Here's the structure of that. All right, now look at some magnetic properties. You know about paramagnetic, right?
That's when all the electrons are paired.
Yeah, all the electrons are paired. Do you know about diamagnetic?
We're not sharing the promoted.
Diamagnetic is at least one unpaired electron. Right?
Wait.
Oh, right. Sorry. They're all paired.
Diamagnetic.
Diamagnetic's all paired. Paramagnetic's at least one unpaired electron. And ferromagnetic is what? Have you ever heard of ferromagnetic? Ferromagnetic, these are like permanent magnets. Right? A paramagnetic material isn't necessarily a permanent magnet, but it will be attracted to magnetic fields. A ferromagnetic material will act like a permanent magnet. And it's not here right now. And so why are some materials ferromagnetic? In particular, iron, cobalt, and nickel. Iron, cobalt, and nickel. Here's cobalt samarium magnets are used in high efficiency motors. This look like speakers. Yeah. And it's thought to do with size. So let's take a look. There are other materials, but if you look at a typical metal atom, let's say it's going to have a net magnetic moment like this. And so, you got some unpaired electrons. It could be 1, 2, 3, and all those unpaired electrons are going to give it a net magnetic moment. We'll just show with an arrow. And so this is like a magnet, a little magnet here. Okay, but in a paramagnetic material, these magnetic moments are randomly oriented. Okay? And so paramagnetic material will be attracted to the magnetic field. Like this. But this is what we have when we have large atoms. When we have atoms that are quite small, what will tend to happen is if this one's up, this one will be down, this will be up, and down. And so if we have small atoms, the magnetic moments will interact with each other like this. But if we have atoms of just the right size, which would be like iron, something like that, then what happens with these magnetic moments is they all line parallel spin like this. And so when all the magnetic moments are lined like this, then there's going to be a permanent north pole and a permanent south pole in this crystal. And so this would be like one crystal of iron. Another crystal of iron, iron's what we typically call polycrystalline. And so the other crystal might be like this, but all the spins are lined up. It's depending on how the crystals came into being like this, right? And then what you could do is you could put this chunk of iron with all these tiny crystals into a strong magnetic field and magnetize it. And so when you put this into a strong magnetic field like this, then these ones are okay, but these ones will be flipped like this. And then pretty soon all these little crystals will have the same magnetic orientation, which means it's been magnetized. And it'll stay like that for a while before it becomes demagnetized and you have to remagnetize it. But in geology, they could see this, and with high iron minerals, they could see this alignment in and it spins according to the Earth's magnetic field. And so you have just the right size. All right, so chapters 21 through 23, there's this interesting, what we call descriptive chemistry, you know, about the elements. There's one thing I did want to talk about, though, this. That is water. Since water is so important, what did I? But maybe I'll just say it verbally. I don't know what happened to it. Do you know how our water is deionized? Is our water distilled? No, we don't use distilled water here. Distilled water is too expensive. Distilled water is too expensive because we would have to use a lot of energy to boil it and then cool it, you know, to capture it. And so distilled water has very high purity. Instead, we deionize our water. How is our water deionized? Is it the same thing as soft water? A soft water, you know what a soft water does is it exchanges what we call hard ions, like 2 plus and 2 minus ions, for soft ions, like 1 plus and 1 minus. You know, and so you're exchanging hard water. Hard water is characterized by having calcium ions, carbonate ions, phosphate, those types of things. Those hard ions tend to form stable precipitates. And so a water softener, what it typically does is it exchanges these through an ion exchange process. So it'll take calcium ions and replace it with 2 sodium ions. It'll take, you know, carbonate and replace it with 2 chloride ions. And so you're replacing problematic ions with less problematic ions, unless, you know, you need low sodium levels, right? Well, our deionized water is different. Our deionized water uses a resin, and in this resin, it exchanges cations for H plus ions, hydronium. And so all the cations that go in there, including sodium ions, are replaced. Actually, I'm surprised this in search doesn't work.
Maybe you change the limit results too. Or you just have a book.
I have the entire book. Let's look at deionized. If this doesn't bring up deionized water, surprise. Did they get rid of that section?
Just do like the
Did I misspell it?
No, just do the first word. Water.
Okay. Page 974. Hang on, page 974. Okay. Well, it's in here. I should have brought my book, but I didn't think. Is this difficult to find? Let me see if I have. Okay, it's going to be here. Well, one thing we were talking about is the hydrogen fuel cell. So unfortunately, I'm sorry, they got rid of it. It was in this chapter here, hydrogen and the environment, hydrogen economy. So, well, anyway, deionized water uses something called an ion exchange column. And it's very And so something like this, we have the resin here, and the resin will just replace, like I said, all the cations with H+, all the anions with OH-. H+ and OH- will just make neutral water. It doesn't get rid of other things, though. For example, what if you have like dissolved organics in there? You know, what do? The ion exchange is not going to get rid of that. And so normally what you have is something like activated carbon. You know what activated carbon is? Activated carbon is just this really porous carbon that has like these tiny pores in it that can fit molecules, and molecules kind of gets trapped in the pore structure of the activated carbon. And so that, but if you really want high purity water, what we used to do, or you know, what I used to do is I took the deionized water and distilled it twice. It's called double distillation. You distill it twice, and then you hit it with UV to make sure nothing grows in it. And then you get very high purity water. And so, but it's very expensive. You know, the cost per gallon of that is really to produce. Okay. You can buy systems for that. I shouldn't have done Wikipedia. We'll just look for a commercial system. All right, so that's a little bit about water and the metals. Okay, now we're going to go to chapter 24. With chapter 24, I'm going to cover it the last section first, and then middle section. And so first we're going to look at the optical and magnetic properties of transition metal complexes. The optical and magnetic properties of transition metal. The optical properties are really weird for transition metal complexes because you could have a cobalt ion, you know, and you think cobalt, okay, maybe it's pink in color or something like that. But depending on what ligand attaches to it, its color can change dramatically. And so you see a huge range of colors for the same ion. And so why is that? And so let's take a look at the origin of the color and the magnetic properties of complexes. This has to do with this. This is the theory that kind of describes, you know, what's happening with the color. It's called crystal field theory. Crystal field theory is the, you know, this often happens with theories. There's a light version, right? And then there's the more in-depth version. crystal field theory is called the light version of this. The more in-depth version, the crystal field theory is kind of like your partial quantum mechanical treatment of these complexes. This would be similar to something you've seen before. You know, what you've seen before is like the difference between valence bond theory and molecular orbital theory. How would you describe those? What's the difference between valence bond theory and molecular orbital theory? Omar, yeah?
Light and full.
The light and the full version, right. Which one is the light version? Which one's the full version? The valence bond is the light version. Yeah, MO is the full version, right? Well, crystal field theory is the light version. The full version is called ligand field theory. Ligand field theory is just a full quantum mechanical treatment of this. And actually the theory, there's only one theory, and that one theory is quantum mechanics, right? And so this is just quantum mechanics applied to complexes, in which they call it either crystal field for the simplified or the ligand field for the more advanced. The difference is how you treat the ligands. You know, in crystal field theory, they treat the ligands as like point charges, you know, just positive. And actually, are ligands positive or negatively charged? Negative, right. Ligands are negatively charged or neutral. And so the ligands come in, well, even if they're neutral, it's electron paired donor, right? And so it's that negative charge density. And so for crystal field theory, the treatment is this. They treat it as just negative charge density coming in. Whereas in ligand field theory, they don't treat it as negative charge density. They look at the MOs, you know, how the bonds are forming. And so, well, what happens in a transition metal? Well, first let's take a look at some transition metals. We've got to look at the electron configurations of the transition metals. So let's look at cobalt, you know, something like cobalt 2+. If you look at cobalt metal, let's just review. What's the electron configuration for cobalt metal? If I look at cobalt metal, it would be argon, what? 4s2, 3d, 3d, it's halfway, 3d7, okay. Argon 4s2, 3d7, is it diamagnetic or paramagnetic? Paramagnetic. Will it conduct electricity? Yeah, as metals do. Okay, now let's say I take cobalt solid and then I do cobalt 2+. What's the electron configuration for cobalt 2+? So this will form cobalt 2+ plus 2 electrons. And the electron configuration for cobalt 2+ is argon 3d7. That's correct, 3d7. That's because we ionize the valence electrons first, the highest end. And so what's happening with the bonding? Now let's attach some ligands to this. Let's do hexamine cobalt. And so if I have hexamine cobalt like this, you know, that means I have how many amine ligands on here? 6. In a, what configuration? Octahedral configuration like this. Let's do some kind of valence bond action here. If we do some valence bond, what's happening? Tell me what's happening with valence bond theory. What's a hybridization on this cobalt in valence bond theory?
sp3d2.
And so what's happening with electrons? show me my 7d electrons. Where are my 7d electrons right now? Where do I draw my 7d electrons? Did those 7d electrons participate in the bonding? Because, what kind of bond is this? Between a ligand and the metal is what we call a coordinate covalent bond. And a coordinate covalent bond means what? Both electrons came from the ligand. And so, so what electrons come from the cobalt? None. And so, you know what? Eventually, you're going to hit this point where you go, wow, valence bond theory doesn't work. Valence bond theory fails. Right? In some cases, you might say, oh, it works, but it clearly fails in many cases. And so valence bond theory doesn't work. And so where are well, how many valence electrons does cobalt 2 plus have? Tell me. How many valence electrons does cobalt 2 plus have? 0. And so what are the E7 electrons? What do we call those? Those are called core electrons, right? And core electrons, do those participate in the bonding? No. The core electrons are what we call non-bonding. And so when we're looking at cobalt, and we aren't going to do the MO theory for cobalt, but there's going to be some bonding, and some anti-bonding up here, bonding down here. But the d electrons are stuck in the middle. The d electrons we call non-bonding. Non-bonding. They're in the core shell of the cobalt. And anyway, there are other electrons participating in the bonding, and those electrons are coming from ammonia, and so there's got to be empty orbitals that those are doing their LCAO with, right? The full MO treatment. Are we going to do the full MO treatment of these? No, this is beyond the scope of this class, right? All we're going to do is we're going to ignore the bonding and the anti-bonding and focus on the non-bonding. The reason we're focusing on the non-bonding, these electrons in the core, is because that's where the optical and magnetic properties for these complexes come from. And so these are non-bonding d orbitals here. And so I have 7 d electrons. Well, those are stuck in here. 1, 2, 3, 4, 5, 6, 7. They're going to be 3 unpaired d electrons in here. But that doesn't mean that these ligands have no influence, because the d electrons are negative, right? And the ligands are donating negative charge. And so what happens is there's repulsions between these non-bonding d electrons and the ligands. This is why it's called crystal field or ligand field theory. And so all we're looking at is the degree of the repulsions between the ligands and these core electrons. And so that's what these diagrams are showing here. And so what we're going to do is we're going to bring in an octahedral field of ligands. We call it an octahedral field because essentially it's an octahedral arrangement of negative charge density that's coming in here, so it's going to generate an octahedral electric field. And so as this octahedral field of ligands comes in, this negative charge, it's going to interact with these non-bonding d orbitals here. We got 5 of them. Now we set up a coordinate system like this, an x, y, z coordinate system. And so we look at how it comes in, and note that if you look on the z coordinate here, a ligand comes straight into this lobe. And ligands come in straight into this hula hoop lobe. Well, when ligands come straight into there, there's negative charge in this d if there's an electron in there. It could be empty, but if there's an electron in here, that's going to be repelled by the negative charge coming in. Right? So it doesn't help. And so this is called the dz squared orbital because it has this distinct shape here. This is called the dx squared minus y squared. if you look at the dx squared minus y squared, there are 4 lobes on the x minus x, z minus, or no, not z, y minus y here. And so as the ligands come in, you see in this plane here, they're going to go straight into the lobes. That's not good. So not good, not good. This is better. Why is this one better at minimizing repulsions?
They don't go straight into it.
Yeah, these ones aren't going straight into the lobes. You see they're going between the lobes. And so that minimizes the repulsion. How about this one? This one is the same as the last one because it's going between the lobes, which is better, right? And finally, this one is the same, between the lobes. And so normally the d orbitals are what we call energetically degenerate. You just draw 5 in a line, right? But what happens is if an octahedral field comes in, it loses its degeneracy and splits. And so this is what happens. This is a free metal ion with no field, no around it. And then we bring a field in here, and we get repulsions, right? And because it's an octahedral field, the dz squared and the dx squared minus y squared get bumped up higher in energy than the other 3 because the ligands are coming straight into the lobes. Now, from the first law of thermal, energy is conserved, so these get bumped up, because we only have 2 of them, they get bumped up higher than these. Get bumped down because we have 3 of these. And so 2 times whatever, 2/3 versus 3 times 1/3 give you the same energy. That splitting is the origin of the magnetic properties and the optical properties of these transition metals. And so there are 2 scenarios, depending on how big the splitting is. The gap here is not called band gap or anything else. This is called the, what is it called? It's called the energy gap. The energy gap has a different name depending on what kind of field we're looking at. This is called the octahedral crystal field splitting energy. Octahedral crystal field splitting energy is a lot of words just to describe this gap here. But it depends on how big the gap is. You know, because we have another energy we have to worry about. And so there are 2 energies we deal with in dealing with these complexes. One energy is this gap. The other energy is called the pairing energy. This gap might not be so big here. And so that means, you know, to pair electrons in a single orbital, you're going to have repulsions, electron-electron repulsions. But those electron-electron repulsions can't be helped if, you know, in order to unpair this has to jump up here because that would have to gain this much energy. But we have 2 scenarios here, and that is this. When the pairing energy is less than the splitting energy, the electrons will pair. When the pairing energy is greater than the splitting energy, the electron will be promoted. And so if we have 4 electrons, we fill it 1, 2, 3 according to Hund's. The 4th electron will either pair or split, depending on how big the gap is.
When you're talking about pairing, you're talking about the electron, the ligand pairing with the...
No. No.
Which electron pairs which?
Not the ligand, the metal. If you have...
Metal have 7D, no, D7.
Okay, this is D4. What metal is D4? Like chromium 2 plus. Chromium 2 plus would be D4. And so this would be like chromium 2 plus. Well, what do you do with that 4th electron? With the 4th D electron, should I pair it or should I promote it? Well, it depends. It depends on what the ligand is, you know. This gap is going to be dictated by how strongly the ligand interacts with the d orbitals. And so we have to look at how the ligands interact with the d orbitals now. The ones that create the strongest electric field are these ones on the left, and the ones that create the weakest electric field are on the right. And so the stronger the electric field, the bigger the splitting. The weaker the field, the smaller the splitting, because there's not much difference, between things. And so we call these strong field ligands versus weak field ligands. And so strong field ligands, big split; weak field ligands, small split. And so this is the summary here I'm going to give you. Strong field ligands are like carbon donors. Carbon donors are the strongest, like cyanide, the lone pair on carbon. Followed by nitrogen donors, followed by oxygen donors, followed by the halogens. The sulfurs we'll just ignore. The sulfurs are, and the nitrogens, let's ignore. Actually, no, let's just ignore the sulfur. So, if we look at cobalt here, cobalt, the hexafluoro, how do I say this? Hexafluorocobaltate 3. Hexafluorocobaltate 3 is what we call a weak field complex. We don't really call it a weak field complex. We typically call it, it's a weak field ligand. And the weak field ligand results in promoting, the splitting. A strong field ligand, like the amine, the hexamine cobalt 3, amine is a strong field, so that means pairing. And so we go back to over here and we look at the two scenarios. This one would be like strong field, right? This would be like the hexamine. This would be the hexafluoro. And so already you see the magnetic properties are different. What's the difference in the magnetic properties? Although this is not cobalt 3. How many d electrons does cobalt 3 have? Can you see? 6. These 6. But anyway, we'll just use it as an example. But you'll see the magnetic properties are different. This one is more paramagnetic because it has more unpaired spins. This one is less paramagnetic. And you can actually measure the difference using a special balance. All right. The other thing is light. When photons of light hit this one, if there's a big gap, I wish they did this with a big gap here. If there's a big gap here, we need higher energy photons, right? What are higher energy photons? Red, orange, yellow, or green, blue, violet? Violet, green, blue, violet. And so what tends to happen with these complexes is they absorb green, blue, and violet. When they absorb green, blue, and violet, do they look green, blue, or violet? No, they look the opposite, right? The opposite color would be red, orange, yellow. And so these complexes are typically red, orange, yellow, low energy colors. These complexes down here absorb red, orange, yellow, and they appear green, blue, violet. And so the colors depend on the ligand, because if you have an amine ligand, it might look red, whereas if you have a fluoro ligand, it's going to look blue or green, And so in other words, absorbed low energy appears high energy, absorbs low energy appears high energy, absorbs high energy appears...
Wait, say that again?
I did. I said it twice by accident. Absorb high energy, it's going to appear low energy. Absorbs low energy, it appears high energy. And we have another name for this. This is called low spin because lower number of spins. This is called high spin. And so I'll summarize that right now. So let's look at just the cobalt-3. So if I have a mean like this, a mean is a strong field or weak field?
Strong.
Yeah, this is strong field ligand. Strong field ligand means a big splitting energy or small splitting energy? Yeah, and we call this delta. And so we say big delta O. O stands for octahedral. Delta is the splitting. Big delta, which means high spin or low spin? Low spin. Which means it absorbs high or low energy light? Absorbs high energy photons, and it appears low energy color. And so what we have is we have these 2 orbitals up here and these 3 orbitals down here. Now, cobalt 3 plus is D6. So what we do is we just fill the orbitals up, right? Oh yeah. So let's fill the orbitals. Why don't you fill the orbitals here? You just fill them just like you did in Chem 1A. These are non-bonding atomic orbitals. And so we apply Hund's rule, 1, 2, 3, and then the 4th one, pair or promote? Pair. 3, 4, 5, 6. Delta's big here, right? Big delta. And this would be diamagnetic. Why is it diamagnetic? They're all paired. Whereas if I had fluoro, let's do that. The hexafluoro complex now. Fluoro is a weak field ligand. And so delta is going to be substantially smaller. The repulsions aren't going to be so big. And so it would be just all the opposite. Rather than strong field, it's going to be weak field. Rather than big delta, it's going to be a small delta. Rather than low spin, it's going to be high spin. Rather than absorbing high energy, it absorbs low energy and appears high energy. And so here we go 1, 2, 3. Now this delta is small enough that it promotes 4, 5, and then finally I have to pair. And so this is going to be highly paramagnetic, whereas that's highly diamagnetic. And the 2 colors are going to be totally different, even though they're both cobalt 3 plus. So let's, we can see some colors here. Actually, here it is. We call P for pairing and then delta O for the splitting. And so there's some colors here. These are cobalt complexes here. And so nitrogen donor is what? Strong? Actually, bromo versus chloro versus iodo. These are all 5 ammonias. And so we're just changing this ligand here. You can see how that. But maybe let's look at the chromium complexes here. You know, aqua, is that a strong field or a weak field? Weak field, or mid field, let's say, but on the weaker side. Aqua, the aqua complex of chromium is violet in color here. But take a look at the mean complex. purple's tricky, but if you look at the mean here, a mean is strong field, so it should absorb higher energy, it appears lower energy. This absorbs higher energy, it appears high energy, right? Do you guys see that? We have to be selective, because then you get into these other effects here, and it gets more and more complex. But keeping it simple, this would be keeping it simple. And that's all you need to know. All right, the simple trends here. Chloro is a weak, right? Which means it absorbs higher, lower, and it should appear higher. Aqua is higher, stronger, and so it should absorb higher and appear lower. Do you see? Do you see something? It doesn't agree, right, here with what I just said. But there's other reasons for this, so don't worry about this one if you're trying to use this one as an example, okay, because this one's more complex. And so just know the simple ones. Okay. Zinc and aluminum are colorless. Why? Zinc and aluminum complexes have no color. No. There's another reason. How many d electrons does zinc 2 plus have? D10. D10 is special because 10 means all the orbitals are filled. Can you put 3 electrons in an orbital? No. And so if each of these orbitals is filled, how can you promote one from here to here? It has to go way up. Way up would be like UV. And so D0 and D10 complexes are colorless. D0 and D10 complexes are colorless because there are no electrons to promote. All right, let's take a look at something else here. Other patterns. Not only do we have octahedral complexes, we also have tetrahedral complexes. Now, the way we're going to bring the ligands here is, in the middle of this quadrant. If we look at the XYZ quadrant and we come straight down in the middle, that's one ligand, another ligand here, another ligand here, another ligand here. And so what happens with tetrahedral complexes is it impacts the opposite orbitals more than the octahedral. The XY, the XZ, and the YZ, being oriented off axis is going to be impacted more than the ones on axis because these ligands aren't coming on axis. Do you see that? And so we get an inverted pattern here. But the thing about tetrahedral complexes is that the ligands do not come directly at any of the orbitals. They all come indirectly. So delta T is a lot smaller than delta O. That is, even with the same ligand, let's say you have a strong field like amine. Well, amine is going to have only 44% of the impact. We call this 4/9. And so delta T is 4/9 delta O. And so this gap is never very big. And so for tetrahedral complexes, it's easy because all tetrahedral complexes are high spin, meaning that all tetrahedral complexes you never pair, you always promote because delta is relatively small. Now delta can change, so it'll change the colors of these, but overall delta is small.
Sir, you mentioned high spin and low spin. What does
High spin means you have to promote the electron to a higher energy. Low spin means you keep the electrons in lower energy. So which one's high spin? Which one's low spin? The left or the right? The left is high spin. The right is low spin. All tetrahedral complexes are high spin because the gap is not big. we have square planar complexes too. The square planar complexes, we bring the ligands on the x and y axes. That means the z is untouched. And so the z, actually, the dx squared minus y squared gets impacted the most. The xy is next, the dz squared is next. Usually we cluster these three about the same. So these are roughly the same. Or you can just leave it like this. Square planar, you can see quite a large splitting here. So square planar, we always do low and fill the orbitals up in this manner. And so low spin. So some things are, some things violate VSEPR. One of the things that might violate VSEPR is like, let's see. When you're looking at electron repulsions, you might say it should be tetrahedral, but it ends up being square planar. Why? Because there's no, normally when you have square planar, you need a pair of electrons on the top and a pair of electrons on the bottom, and you got 4 bonded atoms, right? That gives you square planar. 2 lone pairs, 4 bonded atoms gives you square planar. But in these complexes, all we have are 4 bonded atoms. And if you were to apply VSEPR to it, we'd always say tetrahedral. But the reason why some complexes seem to violate that is because there's an energy savings. So for example, nickel 2+ and platinum 2+ always form square planar. And so you have a nickel 2+ and it's always square planar. Why? Well, it's always square planar because nickel 2+ has how many d electrons? Nickel 2+ has 8 d electrons. 8. Do you guys know the trick? You guys remember this from Chem 1A? Nickel +1 +2, 8, d8. Right? Cobalt +1 +2 +3, d6. Cobalt +1 +2, d7. Iron +3, what is it? Iron +1 +2 +3, d5. And so nickel 2+ is d8. Now, do d8 in this. If I have 8 electrons and I have a tetrahedral complex, I go 1, 2, 3, 4, 5, 6, 7, 8. And so this is filled, half filled, right? And then I look at the total energy of this. The total energy is going to be some kind of, I got some higher energy electrons and some lower energy electrons, and just average it out, right? This is D8. But if nickel 2+ went square planar instead of instead of tetrahedral, this is what happens. Oh, where did I put that? Pass it. There it is. Now, if I do it as a square planar complex, 1, 2, 3, 4, 5, 6, 7, 8. That leaves this highest energy orbital empty. And so when you average this, the energy of electrons versus tetrahedral, this is going to come out lower in energy. And so it doesn't adopt square planar because of VSEPR. It adopts square planar to minimize the d electron energies by leaving one of the d orbitals empty, and that being the highest energy. Whereas every single tetrahedral orbital will be occupied. Does that make sense? Yes? No? Well, we're out of time. So that's it.